every single year on this lesson. I've been looking at my past videos, and I have had to make a video at home, or like my kid has been sick, like for the past 3 years. This is the first time I'm teaching this live in a long time, and I'm super excited because this is a great lesson today. Anyway, let's get to going over the homework. A lot of people were really excited about this lesson. A lot of people in my 7th grade class were very confused about this problem. What I suggested to them, if you didn't want to distribute in the 5/9, you could just divide by 5/9 over to the other side. I actually have the work still on the whiteboard. You would divide by 5/9 over to the other side, which is essentially multiplying by 9/5 over to the other side, right? So if you didn't want this weird messy fraction, 5/9 f minus whatever, 32, what would that be? 32 times 5, whatever. I'm not even going to do that in my head. 32 times 5, and then divided by 9. Does that come out nice? No, that doesn't come out nice. So I'll put it into a fraction, 169. And then we would subtract that over and divide by 5/9. But then I would be dividing by 5/9 to this thing. And then it would come out nice and even at 32. So it does end up getting you back to 32. But the easiest route to take would be to divide by 5/9 right off the bat instead of distributing it in. Which again, dividing is like multiplying by the reciprocal. That's why I changed it into 9/5. See, and then we can just add over the 32. And then it says convert 16 degrees into Fahrenheit. So 9/5 times 16 plus 32 is going to be 60.8 degrees. 60.8 degrees. Bless you. Questions on that one? No. All right. Here is 18, 20, and 22. It's funny. Was I having this conversation with your class about schedules in other classes? Maybe it was 7th period, but we got in this discussion because I was telling them what's coming up, and they were like, "You are the only class that stays to a schedule." Yeah. Is that true?
Yeah.
That was I don't know. Nails on a chalkboard. It's
other teachers are like, "Oh, I'm gonna move the test back today because I completely forgot to go over this."
Right, or something somebody was like, "Oh yeah, we got a quiz tomorrow." You're like,
"Oh, I'm just gonna remove this part from the quiz because you didn't learn it."
Or I don't know. "Oh, I threw something up on Canvas. Go ahead and check that out. Let's do tomorrow."
Yeah.
I can tell you exactly our chapter 7 test is on March 5th.
I know.
Yeah, but not every class is
Next week, probably
But yours is going directly from the book.
Yeah, that's true. That's true. I guess mine is a little bit more structured. Math is more structured. I don't know. Even if I taught a different subject, I would
Yeah, but how would you do that with English?
Set a schedule.
Well, I mean,
Just set a schedule.
Mr. Freeline, he has a reading schedule.
Well, I do have a schedule. It's just you don't know about it until they tell you.
I guess.
Yeah, maybe they know about it. You just maybe.
The hardest part is with this, there's lesson 5-1.
Right, exactly.
With them, it's kind of whatever they.
Read this book.
Yeah.
Let's write this paper.
Yeah.
No, I can't do that.
Exactly.
I could never be an English teacher.
Well, that's just the homework. I think is a big part of it.
Okay, here's 24, 26. Again, the method of finding the inverse is switch x and y and then resolve. Right? Switch x and y, then resolve for y, and that's going to be your inverse. So 24, f of x is really y. So now I change it into x is equal to 145 plus 12.5 y. And then resolve. Subtract the 145, divide each piece by 12.5. And that's x over 12.5 minus 11.6 is equal to y. So that one you could distribute in the 4/5, Or you could divide by 5 or 4/5, which is multiplying by 5/4 over to the other side. And that's where you see that come across in the end. It's just as nice that that one is, when I multiply in the 4/5, I take 4/5 times 15 and it comes out nice. Like this one over here with the degrees didn't come out nice. And then here is 28. Okay. Questions on the homework? Anything that we'd like to go over? Okay, right. I'll leave that up there for a second. So today, again, I'm really excited about today. We get to talk about logarithms. It's the first time you guys have ever seen logarithms. Some of you guys are going to find logarithms easy. Because, again, it's one of those things in math that you learn the rules, you follow the rules, you get the right answer. Okay, and I know some of you guys really like that. You learn the rules, you follow the rules, you get the right answer in the end. You just got to learn the rules, and that's where some of you may not like working with logarithms. Because you just got to learn a new set of rules. Now, the nice thing is the rules tie right in with exponential rules, which we'll talk a little bit more about section 7.4. Okay, let me ask you this. If I gave you $1 and I said I was going to double your money, like I know we did this the other day where I said I was going to give you $10 a month or $10, double it every month. If I gave you $1 and I said I was going to double it every month, how long would it take you to get to $8? Well, that'd be pretty easy to find out, right? I can just manually figure that out. You know, I get that one time is $2. Second time is $4. Third time is $8. So I'd have to double it 3 times, right? That's a really easy one to figure out. But what if it wasn't so easy? What if I gave you a giant number that it would be really hard? You'd have to actually take the time to figure out, go through and say okay, this is what it would be at doubling once, twice, 3 times, 4 times. And keep going and keep going and keep going. And what would happen if it came out to an uneven value? What happened if it came out in the middle of something? Okay? That idea of figuring out how many times it's going to take you to do that we're going to need a logarithm to solve. Okay? How many times would you have to double $1 before you had $8? We talked about that. We could use an exponential equation to model that situation. Think about it. 1 is my original value. 1 is my starting value. I gave you $1, and I'm going to double it every time period. So doubling means 2. 2 is my base. I'm basically giving you 100% interest, right? So 2 to the x power. And I want to know when that's going to equal to 8. Before, back in section 7.1, all we knew how to do here was just plug that into our calculator and say, okay, this is y1, 2 to the x, this is y2, 8, and I see where those 2 lines cross. And I evaluated that. I find the intersection pointed out. Okay. But again, we may be able to solve this equation just by using mental math, figuring out, okay, now 2 to the third is going to equal 8. Now, how many times would you have to double $1 to get to 512? See, if I give you a big number like 512, yeah, I bet you could still go through and actually figure it out. And figure it out, okay, 2 to the x power would be 5 to the 512, and actually see what would happen with x. Basically, what I'm looking for here is the inverse operation to get x out of the exponent, right? What gets x out of the exponent? How do I solve this equation? How do I take 2 to the x power is equal to 512? How do I solve for x? A lot of people might try to tell me, oh, you got to use a square root. No, remember, a square root was if I had a squared power. So to undo a squared, I'd have to take the square root. But it's not just a number up in the exponent, it's a variable up in the exponent. Okay, it's an x up in the exponent. So would I take the x root? No, not necessarily. What we have to use is called a logarithm. The operation of taking that power out of the exponent is called a logarithm. It's an operation. It's a new operation, just like add, subtract, multiply, divide, square root, absolute value, cube root, logarithm. Logarithm. It's a new operation. A logarithm is the exponent, and I would underline that word, is. a logarithm is the exponent. That's really weird to say. A logarithm is the exponent to which a specified base is raised. The logarithm is really equal to the exponent. A logarithm is the exponent to which a specified base is raised to obtain a given value. Okay, so basics, the logarithm is the exponent. It's an operation to solve for that value within the exponent. Okay? Now, here's how we transfer from logarithmic form into exponential form, and vice versa. Taking exponential form into logarithmic form and logarithmic form into exponential form. So take a look here. I've got b to the x is equal to a. This is our standard form for an exponential equation, like 2 to the third is equal to 8, right? What I would do is take the logarithm, abbreviated log base b, and that's how we would read that, log base b of a is equal to x. That's how we read that. Log base b of a is equal to x. How did we get that? Well, the base of the log is the base of the exponent. So if it was like 2 to the third, the 2 is my base of the exponent, so the 2 is the base of the log. It's written as a subscript underneath log, okay? Just down below. So it's log base b, and now it's going to be of whatever you were equal to, okay? So this a now gets operated on with the log base b of a. Every time you have a logarithm, you have to say a base. Okay, the base can change, just like the base of an exponent can change. The base of a logarithm can change. It's referenced by different numbers. You can have log base b, log base 2, log base 10, log base 7, log base 3. You can have all sorts of different log bases because you can have all sorts of different exponent bases. Okay? So you have to define what the log base is. Log base b of a is equal to x. Remember, the logarithm is equal to the exponent. The logarithm is the exponent. It's the operation that will evaluate to give you the exponent, to which that base is raised. Okay? Now, somebody said to me a long time ago when I started teaching on Algebra 2, they were like, oh, Mr. Lavick, it works kind of like in a spiral. I was like, what are you talking about? He said, well, if you take if you take b, it's log base b of a is equal to x. Okay, I got that. Okay, that sounds good. And if you wanted to go backward, you start with the base and you say, and if you, again, trying to work backward, trying to put it back into exponential form, b to the x is equal to a. It kind of like works in a spiral in that way, if you wanted to rewrite it in the other forms. Because it may be helpful, for you guys, once you're starting out in logarithms, to transfer it back into exponential so your brains can work on it. You might have to transfer it back into logarithmic form, but at least you can kind of understand what's happening when it's in exponential form. Kind of like, when you learn a new language and you don't think in that language, right? You have to transfer it back to English, think about it, and then put it back into German or whatever, right? You don't think in that language. You're going to have to, if I give you something with a logarithm, you might have to transfer it back into exponential to think about it, and then put it back into logarithmic in the end, okay? And again, you can work both forward and backward. Okay, so let's think about some general powers. Like I'm gonna make some in exponential form. Let's say like 2 to the, no, let's not do 2. We already did a log base 2. Let's say 3 squared is equal to 9. Let's say 4 to the third power is equal to 64. And then let's say 7 to the 0 power is 1. Okay. Those are all powers that we know of, right? 3 squared is 9, 4 to the third is 64. Those things are, those things are just, common sense, right? 3 squared is 9, 4 to the third is 64, 7 to the 0 is 1. So how do we change those into exponential form? Well, what we would do is we would go up to take our spiral, base b of 9 is 2. Log base 3 of 9 is 2. That's how we would write that. Log base 3 of 9 is 2. Log base 3 of 9 is 2. Log base 4 of 64 is 3. Log base 4 of 64 is 3. Log base 7 of 1 is 0. Log base 7 of 1 is 0. Okay, that's how those transfer. Okay? Let's practice that a little bit. Why don't you guys, what does this say down here? Oh yeah, we've been saying that all along. All right, why don't you guys try those top, well, why don't you try all of them real quick? We just did a bunch of examples. Why don't you guys try these 4? Again, we're just translating. Like I gave you a list of vocab words and you're translating from English to Spanish or something. Or German or French or Latin. You know what you thought for Latin? Yeah. I think it was just like 5 years ago that they stopped talking Latin. Okay, check your answers there. Okay. Log base 3 of 243 is 5. Log base 25 of 5 is 1/2. Log base 6 of 1/6 is -1. Log base A of C is B. Now, think about what we have here. Like, okay, you know, if I gave this to you in logarithmic form, or if I didn't know what this answer was, and I said evaluate log base 3 of 243, what you're really doing there is saying 3 to the what power is 243? And then you could just calculate it out. Okay, 3 to the 5th power is 243. So log base 3 of 243 is 5. Okay, you can evaluate that out. Think about this. 6 to the 1/6, or 6 to the what power is 1/6. Well, what puts it down into the denominator? A negative exponent. So that must mean that evaluates to be a negative number. Okay, if you ever have the logarithm of a fraction or of a decimal, it's probably going to come out to be negative. Okay, now let's transfer it back. Let's go backward now. Go ahead and do these 4. Transfer it from logarithmic form into exponential form. Remember, start with the base, exponent equal to. I'll do the first one here for you. You know what? Let me do B, because that one's weird with the 9s. Start with the base around here. So this is log base 8. So the exponent base is 8. It's equal to 1/3, and it's always equal to the exponent. So it's 8 to the 1/3 is 2. Okay, do the other 3. Just transfer it from logarithmic form into exponential. Nine to the 1st is 9. 1/16 to the -2nd. Oh, sorry, excuse me. 4 to the -2nd. I thought it was the of number. 4 to the -2nd is 1/16. B to the 0 is 1. Okay, questions about that? So that's how we transfer. That's how we translate from logarithmic form into exponential form. I would always strongly suggest to you, if you don't know what's happening with the logarithm, try turning it into exponential and think about it a little bit, because you might be able to tell what's going on with the logarithm based on its exponential form. A logarithm is an exponent, so the rules of exponents apply directly to logarithms. Okay, the rules of exponents, and that's pretty much all section 7.4 is just learning the rules about logarithms. But these are just some special properties of logarithms. This first one here, log base b of b, the log base b of b property. If you ever have the log base and the of number, log base 2 of 2, log base 7 of 7, log base 3 of 3, that's always going to be equal to 1. Why is that the case? Well, because remember, I'm looking for the exponent, and I'm saying b to the what power is b? Well, what doesn't change it in terms of the exponent? The exponent of 1, right? So log base 2 of 2, 1. Log base 7 of 7, 1. Log base 10 of 10, 1. Okay, it's always the same log base. I'm sorry, if it's the same log base as number, then it's always equal to 1. Now, this is the logarithm of 1 property. This basically says that whenever you have log base b, log base anything of 1, it's always equal to 0. Why is that the case? Because I'm looking for what power makes it equal to 1. Right? What power will always make it equal to 1? Raising something to the 0 power. Okay, raising something to the 0 power. So log base 10 of 1, 0. Log base 7 of 1, 0. Log base 1,000,000 of 1, 0. Okay? That's kind of like that 0 exponent property. Whenever I raise something to the 0 power, it's always equal to 1. Yeah, the same kind of thing here. Whenever the exponent is equal to 0, it always ends up being 1. Another thing here is called a common logarithm. A common logarithm. A logarithm with a base of 10. Some logarithms with specific bases have unique names. Like once we get to section 7.5 or 7.6, we're going to learn about the natural logarithm, log base e. But this is called log base 10, common logarithm. A common logarithm is called log base 10. If no base is written for a logarithm, the base is assumed to actually be 10. Like if I said this, log base nothing of 7. If I just said log 7, it's assumed to be log base 10 of 7. Okay, log base 10 of 7. If I just said log of 100, that's log base 10 of 100. Let me ask you this. What does that equal? Can someone tell me? What is log of 100? 2, very good. 2. I'm looking for the exponent to which 10 is raised. How do I know 10? Well, because it's not there. It's not written. So I'm looking for the exponent to which 10 is raised to get to 100. 2. 10 squared is 100. So this is actually equal to 2. Okay. All right. Let's do that a little bit more. Let's evaluate using mental math. Now, I'm sorry, I didn't even talk about why we use common logarithms. Because it's actually right there in your calculator. You ever just see the log button on the left side? That's common log. So like log of 100, your calculator will actually evaluate that. That's just 2. Right? Now, your calculator is a lot more fancy than my calculators. Your calculators will actually evaluate different log bases. My calculator won't. That was an update a couple years ago. You guys can actually create a new log base. I cannot. I gotta figure out a way around it. Right? Evaluate by using mental math. All right, log base 5 of 125. And also, just fair warning, this next quiz, the section 7.1 to 7.4 quiz, is part calculator, part no calculator, and not just red calculator. It's like no calculator, but brain. Just no calculator. So like this, I could ask this on a no calculator quiz. What would this be? 3. 3. This would be equal to 3. Why is that the case? Well, because I'm looking at 5 to the what power is 125. And if I'm asking you to do it in mental math, it's obviously not going to be a decimal. 5 squared is 25. 25 times 5 is 125. 5 to the third power is 125. So log base 5 of 125 is just 3. 3 is my answer. Same thing here. I could x this, no problem. -1. -1. This would be equal to -1. Here's why. You would think about this. 5 to the what power is 1/5. Oh, negative exponent puts it into the denominator, so it would be a -1 exponent. Okay. Let's start to get real fancy. What do we think? You might need to put it into exponential form to figure out what this is going to be equal to. That's a common log, right? So it's log base 10 because it's not written. 10 to the what power is 0.00001. 10 to the what power is that? -1, 2, 3. -1, 2, 3, 4, 5. -5. 10 to the -5th power. So that means that this is actually equal to -5. Why do I have to give this to you on a no calculator thing? Well, because look, you can just plug that in. Look at log of 0.00001. Yeah, -5. Okay. And I want to know that you know how that's working. So let's talk about logarithmic functions. What does it look like on a graph? What does this thing actually look like on a graph? And how does this tie into this whole inverse thing that we learned yesterday? Why was it so important that we learn inverses? Well, because logarithms are inverses of exponents, the inverse of an exponential function, such as y is 2 to the x, is a logarithm. Think about it this way. If I asked you, I'm going to have to write this small. I've got y is equal 2 to the x, and I wanted to find the inverse of that function. Well, you would just flip x and y and resolve, right? That's what we learned yesterday. Okay, x is equal to 2 to the y. Well, if I wanted to solve for y, I'm solving for something in an exponent. I need to turn it into the logarithm. Log base 2 of x is equal to y. And that's where y is equal to log base 2 of x comes in. Okay, the base of the exponent is the base of the log. Log 2 to the x is the inverse of log base 2 of x. Okay, now think about what the exponential function looked like. Think about the parent exponential. The parent exponential is in blue here. Whoa, did not want that. The parent exponential is in blue here. Y is equal to 2 to the x. Take a look at what the logarithm will look like. Log base 2 of x. What do we see here? It's a reflection over the line y equals x. Was this something that we learned yesterday? It's got to be a reflection over the line y equals x. Also, where was the asymptote in an exponential function? Where was the asymptote? Wasn't it the x-axis? So if I'm inverting that, where is the asymptote now? The y-axis. So the inverse of an exponential, because the x-axis was the asymptote, since now the inverse of an exponential is a logarithm, I invert that. Now the asymptote is no longer going to be the x-axis, but it's the y-axis for any logarithm. It's no longer a horizontal asymptote, it's actually a vertical asymptote. Now what does that mean? Well, the domains and ranges will also flip. The domain of the exponential was going to go on forever left and right. So that means my range of my logarithm is going to be all real numbers. It's going to go forever up and down. The range of my exponential was only greater than 0. Look at my blue line. It was gonna go closer and closer to 0, but never reach it, right? So the range of my exponential was all greater than 0. So that must mean my domain of my logarithm is all greater than 0. Okay? So the domains and ranges flip because, again, they are inverses of one another. Okay? They are inverses of one another. So you've got to think about how does the domain of the exponential relate to the range of the logarithm, right? They're equivalent. The domain of the exponential is equal to the range of the logarithm. The range of the exponential is equal to the domain of the logarithm. Okay? And again, the asymptote. Don't forget about that. So what am I going to look for when I ask you to graph a logarithm? I'm going to look for where does it cross the x-axis? Because remember, the important piece was where does it cross the y-axis for an exponential? Where does it cross the x-axis? And make sure that you don't cross that asymptote. Okay, so let's take a look here. Use the x values -2, -1, 0, 1, and 2. Graph the function, find its inverse, describe the domain and range of the inverse function. So see how the example here is only asking about the domain and range of the inverse? I don't necessarily have to do the domain and range of the regular. I just want the domain and range of the inverse. All right, let's fill in our table here. I've got 1.25 to the x power. So 1.25 to the -1 is 0.8. What's anything to the 0 power? 1. Anything to the first power is itself. And now we calculate 1.25 to the second power. 1.56. 1.5625, but you get the idea. Let's graph that real quick. So we've got -2, comma 0.64. A little bit above half. -1, comma 0.8, 0, comma 1, 1, comma 1.25, 2, comma 1.6. Let's, for good measure, do one more point. 1.25 to the third, because we almost can't see that it's growing exponentially. 1.9. Okay, now we really can't, can we? What about 4? What about 4? 1.25 to the fourth. 2.44. Okay. Somewhere up here. Right? So there's our growth. And it is exponential growth, right? How do I know that it's exponential growth? And not decay? Because it's going up, but what did my equation tell me is growth? It's greater than 1. The base is greater than 1. 1.25. So key things that I would look for in this graph. Make sure that it crossed the y-axis at the right part. And make sure that it didn't cross over the asymptote. Right? So if you went below the x-axis, I would take off 1. All right, now, how does this relate to the logarithm? Well, remember that it was, move my table up a little bit. It was y is equal to 1.25 to the x power. So now I'm going to flip x and y. X is equal to 1.25y to the y, excuse me. And now I'm going to resolve for y. I need to get y out of the exponent. And to do so, I make a logarithm. Base of the exponent is base of the log. So it's log base 1.25. Always start at your base when you're making your spiral. Log base 1.25 of x is equal to y. And that's my new equation. Log base 1.25 of x is y. Now, it asks me about my domain and range. Well, remember, I mean, it told me to use -2, -1, 0, 1, and 2. What am I getting at here? I'm getting at the domain of the exponential is going to be the range of the logarithm, and the range of the logarithm is going to be the domain of the exponential. Like so. Look, my table's already filled in. Is yours? No, you don't even have to. But essentially, what did I do? I just flipped the x and y values. I didn't recalculate anything. All I did was just take, okay, now the y value was -2, 0.64. So it's 0.64, -2. Because right now we don't know how to evaluate. In our calculators, we don't know how to evaluate log base 1.25. Like my calculator doesn't even do log base 1.25. Yours does. But my calculator doesn't even do that, so I can't possibly evaluate that yet. So I've got to evaluate the exponential and then switch the x and y. So what does that mean? Well, now my asymptote will no longer be the x-axis, but the y-axis. 0.64, -2. 0.8, -1. 0, 1. You have 1, 0. 1.25, 1. 1.56, comma 2. What was it? 3 comma, what were those numbers? 3 comma 1.95. Right, so 1.95 comma 3. And then it was like 2.44 comma 4. All right, so there is our logarithm. Confirmed by the reflection over the line y equals x, right? I mean, I know it kind of just a general sketch, but pretty good in terms of the reflection, right? Crossing right on that line y equals x. Every exponential logarithm should look like that. Right? Every exponential logarithm, as long as they have the same base, should look like that. They should have a reflection over the line y equals x. Okay. Last problem that we got here is a application. It's one of the many applications we can use with logarithms. Acidity is measured in pH as given by pH is equal to the negative log of the H positive. It says where H positive represents the hydrogen ion concentration. Let me ask you this. What is the base of my log within that formula? What's the base of the log in that formula? Not H. 10, right? It's common log. Log base 10, negative log of base 10, sorry, negative log base 10 of the H positive hydrogen ion concentration. Okay, so it's just basically asking me, this is how you calculate pH. You find this hydrogen ion concentration and you run the negative log of it. All right, so if I wanted to find the pH of milk and I observed that it was 0.0, 1, 2, 3, 4, 5, 6 zeros. Negative log 0.1, 2, 3, 4, 5, 6. Double check. 1, 2, 3. Okay, good. 2, 5. What would you estimate that to be? The pH of milk? Something low, right? Or no, high. I'm sorry. More acidic is low, right? So something higher. Yeah. 6.6. Oh, that's a highlighter. 6.6. Isn't 7 neutral? Isn't that the number? Yeah. Negative log of 0.000316. So tomatoes going to be a smaller number, right? More acidic. 4.5. Lemon juice. Oh yeah, that's it. Negative log of 0.0063. 2.2. Okay. Just one of the examples that you can use with logarithm. I've actually seen, we got a couple minutes left. I've actually seen, in terms of the pandemic, what's been happening, when we see exponential growth, like what we saw back in April, a lot of people were making the Y scale as what's called a logarithmic scale. Yeah, a base 10 scale. Because then if you transfer an exponential growth into a base 10 scale, it turns from a curve, a fast curve, to something that looks a little bit more linear. Yeah? And that's how you can really see the growth of something going at an exponential rate. And as soon as that line tips more downward, then the exponential growth is actually leveling off. Maybe I'll bring up a graph of that tomorrow. All right, so long everybody at home. Shout out Aaron, shout out Hope.